Um, okay, so as far as the quiz is concerned, we're going to have a quiz tomorrow. So the 7 teams will work as a two-man team, two-person team. So make sure there's no correlation because I'm going to have a viva on this because otherwise I cannot be sure about the work. So even though you might be, I will be able to find out.
Excuse me, sir.
Yeah, go ahead.
So is it
Yeah,
okay
go
if
ahead.
we do it next week? This week has been very hectic. We have two quizzes today as well. So is
I
it
see.
okay if
Okay,
we
so
do it
is
next
it
week?
Monday okay? Monday okay then?
Yes, sir. Monday would be fine. Yes.
Monday is fine?
Yes, sir. Yes, sir. Monday would be fine.
Yeah, that's fine. No problem. Yeah, that's okay. I mean, I didn't know. So, yeah, if you're suggesting that, that'll be fine. Monday will be fine. So you will have time also to prepare. So there's just 3 problems in 1 hour. See what happens. So, okay. All right. That's okay. Not a problem. So Monday with the quiz. All
Excuse
right.
me, sir.
Now, go ahead.
Sir, you mean our Monday or your Monday?
Oh, I'm sorry. You're Tuesday. I'm sorry about that. My Monday. Sorry. You always I get confused. Yeah, yours Tuesday. Next week. Next week, the first class. So Tuesday. Uh, Now, yesterday, a couple of people came a little late to the class. One came just about 10 minutes before the class ended. So if that's what is, you don't have to come to the class because you're not going to learn anything attending by 10 minutes. So if you're attending, make sure that you come within reasonable time. So uh, I'm not insisting that, but you don't want to miss anything. These days it's not recorded automatically. I don't know whether you ever tried to get the recording, but I don't see it unless I make an effort. It doesn't get into the stream, so I don't know. So I'm still going to continue to give the testing in forms, but this time in the forms you will have to submit because it's all full question, not multiple choice. So you have to submit after you do the problem in a paper. So one per team. So and then, but I would like to when you finish, even though it might take a little bit more to scan and send, when you finish your paper, I would like you to submit your question paper. So I know that you already submitted it. And I know the timing, the stamping of the time and everything. So I just want to know all that. So when you finish your exam, you're ready to scan, please send your question paper, submit it. Okay, that's why. Is that is there any question on that? Okay. All right. Yesterday we had a issue there. Um, okay. Basically, so let me just explain that. There was a question there. Why? How that the we are taking the non-dimensional thing for T star. Okay. So let me just make it clear there. So there won't be any problem. Okay. So the problem is we have a plate. This is the temperature Ts, and this is the velocity profile. So this is like a delta, and the temperature profile is something. Uh, so at some x from there, it's reaching that. Now this is the T infinity. This is Ts. So we're going to non-dimensional like T star. Non-dimensional temperature is. I'm going to multiply T. I'm going to convert that. All temperature is going to be, the Ts will be subtracted. I tell you why I'm doing that. So you find T star goes to 0 at y is equal to 0. So this is y. So at y is equal to 0, T is Ts, so it goes to 0. And T star goes to 1 as y goes to infinity. Large y, beyond that it reaches T star is 1. So that is the reason we convert that into non-dimensional quantity like this. So, okay, so I want to know how the convective heat transfer coefficient is to be defined in terms of this non-dimensional quantity. So it's basically, what is this? It's Q, uh, Q divided by delta T, or Q divided by uh, T S minus T infinity. Because Ts happens to be bigger than T. Okay. All right. Now Q happens to be minus K of the fluid dt dy. Okay. I'm going to convert T to T star. So I'm going to divide, subtract T minus Ty, nothing happens. So you're dividing, so you're multiplying this. So it will be like this. So dt dy will becomes dt star. So dt star over dy. So divided by t. So I'm going to have to multiply this by t d over minus ts. I'm sorry, t infinity over ts. And y is, I'm going to multiply by the L. So Ly, in other words, y divided by L will be, so multiply by L. So L has to come here. Okay. So that's the, so this, and then I have to divide by Ts minus T. So that's going to be my HC. This is going to be HC. So HC L over K df T at y is equal to 0. What happened here? T infinity, this becomes minus 1. So it becomes dt star over dy star at y star is 0. So this is nothing but the Nusselt's number based on the length scale L. Okay, so that is how I got that curve. So if I can plot my Nusselt's number as a function of Reynolds number, so I get some sort of a curve for a lot of data and so on, and I get some fit, at least up to 100. So up to this one is fairly good. I showed you that last time. Any questions on that? So that is how we got the equation for Nusselt's number in terms of non-dimensional quantity. Nusselt's number is a non-dimensional quantity, and right hand side here is also non-dimensional quantity. Understand? Okay. Okay. So this is how that curve came, and only thing is, since the Prandtl number changes for various fluids, how do I bring the coalesce all the data is if I happen to divide that by the Prandtl number to the power of 0.3, I seem to be getting much better correlation. You know, the mean curve is like 0.82, Reynolds number to the power of 0.4. So you will typically see Nusselt number is 0.82, Reynolds number 0.4, multiplied by PR3. In other words, let me just show that it's basically 0.82 Nusselt's number. So for this particular very small flow up to 100 Nusselt's number, I'm sorry, is 0.82 Reynolds number to the power of 0.4 to the power of 2/3. Is it 2/3 or let me check. No, 0.3, I'm sorry. So it's like 0.3. So once I can calculate in any fluid, if I suppose I want you to calculate my heat transfer coefficient. Okay, I want to get the heat transfer, maybe average one, I don't know. So you give it all the properties of the fluid, calculate the Reynolds number. You can get the Prandtl number is nothing but mu Cp over K of the fluid, all fluid. Calculate that, take the 0.3, and you know that it's the some characteristic length or X, it doesn't matter, the K fluid. So Hc is Kf, whatever this number was, this number, let's assume I got some sort of alpha. So divided by F. So that is how you calculate the heat transfer coefficient to compute my heat transfer due to convection and so on and so forth. So anyway, this is very laminar flow, very low velocity. So, but still the average. So these are all based on the length x. If I average that over the whole length of a structure, a linear plate or whatever, then x disappears. I get according to the total length and an average heat transfer coefficient. You typically will calculate the average heat transfer coefficient so that it would be independent of the distance. And the Reynolds number is also will be calculated based on the length of the plate, and Prandtl number, it doesn't involve any dimension, just mu Cp properties of the fluid, that's all. Understood? Any questions on that? Okay, I just touched upon all the non-dimensional parameters that you encounter in heat transfer. You may want to review that. And as we go further, you will be able to identify where they come across and you can use them. Okay. All right. Now, as I mentioned, the Navier-Stokes equation has not been solved for a number of problems. It's solved only very few problems. One of them is the Poiseuille flow, which is very low velocity. If that's a low velocity, so let me just show you what other thing we are doing here. Okay, so that these are the two equations that I'm getting. How are we getting these two equations? We simplify the original two-dimensional equation. Now, this is we are looking at the between parallel plates. Okay, it's not a pipe or something like that. So I want to get the fully developed flow. This is two parallel plates are there, and the flow is across going. So x and y direction, two-dimensional flow. So here there is a pressure here, gradient, so that, but du dy changes, but once it's developed, it doesn't change from left. Fully developed flow, it doesn't change with respect to x. So all the du dx term on the left-hand side all disappeared. So left-hand side of the equation, so let me just remind you what am I talking about. Just so that I will, okay, so let me just show this. Okay, so let's see. Okay, so here, I don't know why I'm not able to see that one. So I want to just do this. Shoot. Okay, that's all right. I'll just do it. Somehow it's disappearing. Okay, that's fine. So basically, in this parallel flow between two plates. So u du dx, v du dy is minus 1 over rho dp dx plus nu d square u over dy square. So that is my two dimension. Now, of course, the continuity equation is of course valid. Now, u does not change with respect to x anymore because it's under the plate, so that's 0. Du v, because it is going to be, see, du dx is 0, so dv dy is 0. It doesn't change with respect, but v is 0 at both the boundaries, so this is 0. So the left hand side becomes 0. So u is only a function of y only. So that is the reason we only get 0 is minus rho. P is only varying function of x, and u is a function of y only. So that is my momentum equation. So what does it tell you? This is the moment. This is a basically friction based. There is a pressure being applied, gradient, so that it is opposing the frictional forces. That's really what it is. That's what the whole equation is. So let's go back. So how did I? What am I solving there for? Now dp dy. The next equation again. The u is 0, and so the only equation I have dp dy is 0. So the second equation, depending upon the v direction, since identically left hand side is 0, so dp dy. So pressure does not change with respect to y, it only changes with respect to x, because that's a driving force for the flow to occur. So I can integrate this equation, second order equation. Left hand side is, so if I double integrate, I get y square over 2. In other words, I double integrate this twice. So dp dx is a constant. In other words, because dp dy is 0, dp dx is there's a constant pressure. It doesn't, pressure does not, d square p does not change. The gradient is the same. So dp dx is a constant. So I can integrate. So I get y square over 2 mu over rho. You know, mu is taken, rho is taken over here. So mu u ay plus b. There are two constants coming. Everybody understood that, how I did it? Okay, so let's just do that. So here, so the next equation, as I said, u dv over dx, v dv dy is minus 1 over rho dp dy plus nu d square v over dy square. So that is my second equation for the velocity v. Now, we found out from this equation, because du dx is 0, fully developed flow, dv di is 0. So the dv dy, this is 0. And v has to be 0 on both ends. So dv dx is also 0. V is identically 0. So left hand became 0. So v is 0. So that is how we got. So dp dy is 0. Okay. So p is only a function of x. And we are going to assume that dp dx is a constant. There's a constant gradient to supply the energy for the flow to occur. Okay. So that is how the second equation came about. All right. So I'm integrating this, I get this equation. So the boundary condition is both the boundaries. So remember, it's a flat plate, two flat plates, and at u is, so I consider the width to be 2b. Okay, the twice the breadth. So basically, I'm having this b, this width is, length is L, and then width is 2b. It's minus b to plus b, just to give you some geometry there. I'm moving the top plate with respect to u, that's a boundary condition. So u is u and y is 2b. if I provide that boundary condition for this equation, I can solve the u velocity profile. It will be yu over 2b minus yu dp dx b minus y2. Look at, see whether what happens. That y is equal to 0. This is 0. So this is 0. So obviously 0. At y is equal to 2b, u minus, this is y is equal to 2b, this disappears. So u becomes u. So it satisfies the boundary condition. The next is I'm going to calculate what do they mean total flow across this channel, so-called channel. Remember, perpendicular to the plate here, it's infinite. Okay, there's no flow across the perpendicular to the plate. Only flow is in the plane. So u dy 0 to 2b will be total flow. So I can integrate that because I know u. I can integrate over 2b. And if I want to calculate the average velocity, because unit depth, I'm going to consider unit depth as an area will be 2b multiplied by 1. So q over the cross-sectional area. So this is going to be my average velocity. So I can calculate the average velocity, and I know exactly I can calculate the shear stress at this particular point because of the flow and because of the viscosity I will have. The shear stress will be the slope of this u curve here at du dy at y is 0 multiplied by the viscosity will be my shear stress. Okay, now the same way I'm going to be doing a little bit more interesting problem of a flight in a pipe flow. Same situation as far as the flow is considered, very low flow. So what do I do here? What is my equation here? So you have to be very careful. In a pipe flow, so again, I have UR, U theta, and that's it. In other words, UR and U theta, UX, let's say. In other words, R theta, X is my coordinate system. R theta, instead of Z, I just consider X. So my equation is going to be, the UR equation is going to be UR DUR dx U theta du over dy or d theta r d theta should be r, I'm sorry, and it should be ur and ux d over dx ux. Okay, so it's not changing, so this is 0. You obviously in the pipe it's not changing with respect to r. There's no change in the direction, the theta direction, because you cannot satisfy the continuity equation. So the left hand side is 0, is minus 1 over p dp dr. Now this becomes del square, so it's like 1 over r d over r du. Let's assume u to be ur. Okay, let's make it easier. So that is my governing equation. The theta direction again is 0, so I don't have to worry about it. So this is my momentum equation, and there is a pressure. I'm sorry, it should be P dx. P dr is 0. The only direction is P dx will be the only. So this is also 0. So that's if you look at the equation here. So the only direction I have, non-zero, on the whole equation is dp dx. All other directions are going to be 0. So dp, in other words, the gradient of dp, p, the only direction I will have is x. That's the only thing I will be non-zero. So independent of that. So p is only function of x, u and function of r. Okay, so there is in the z direction, there is going to be a pressure gradient so that I can drive. There is no pressure variation in the r direction. Again, just like the flat plate, I can integrate this twice. This becomes this. Okay, so let's say, how will you do this? So let's just do that quickly. So dp dx So 0 is minus 1 over rho dp dx plus 1 over r. So everything is only a function of, u is only a function of r. So I can take total differential. Okay, so I bring it up to, so rho multiplied by nu, this will becomes, so it should be nu here. So rho and nu will be mu, I'm sorry. So mu over r d over dr so dp dx. So this is a constant. This is a constant. So I multiply this by r 1 over mu and integrate again. So r du dr is 1 over u dp dx r square plus a constant a. Integrate again. So this is divided by r. So if I integrate this, let's say, so r du dr, okay. So r du dr is minus 1 over 2 mu dp dx r plus a over r plus b. This is u dr. So you multiply this again, u of r is minus 1 over 4, should be mu will be on the denominator. A log r b dr. So obviously at r is equal to 0, it has to be, so a has to be 0. So I get the velocity profile is minus mu over 4 dp dx r square br plus c. Now at r is equal to 0, so okay, so this is u. R is equal to du. So this, because of the symmetry here involved, so that's a pipe. So at r is equal to 0 here, you got to, so du dr is 0. So you go here, r is equal to 0, this is not 0. So b has to be, I'm sorry, c has to be 0. Du dr is, wait a minute, b has to be 0, not c, not c. In other words, du dr, r is 0, this b has to be 0. Okay, so in that case, and how about at r is equal to r, let's assume is a direction a, so r is equal to a, u is 0. So let's say 0 mu dp dx a square is plus c. So c is mu over 4 dp dx a square. So I can bring that over here. So my ur is going to be, I can bring the mu over 4 dp dx and a square minus r square. So it's going to be parabolic and this constant here. So this satisfies du dr be at r is equal to 0. This goes obviously 0 and r is equal to a is going to go 0. So anyway, that's what we proved. So let's say, how about the u max? So how about the q? So let's just calculate just the way we did earlier. Okay, so all right, so I think I did not do this one very carefully here. So yeah, I calculate already. I can bring in minus here. So parabolic distribution here, dp dx. So a has to be brought the other side. It's okay, not a problem. Okay, now I want to calculate what is the total flow. So how will I calculate that? So I have to integrate 2 pi r dr multiplied by u. So I get, so let's just do that because we don't want to miss anything here. So I want to bring over here. I don't know why that's disappearing. That doesn't make any sense to me. All right, that's okay. So let me just, so u has to be, what did I do here? His minus, it has to be plus. So dp dx, so b becomes c because c is r square. C is a square. So that's okay. I think I'm making a mistake here. So u, so what is my total flow? So ur is basically u over mu over 4 dp dx a square minus r square. Okay, so what is my total flow through the pipe? 0 to a ur 2 pi r dr. Listen, in other words, I have the cross sectional at any r. So this area is 2 pi r dr. That's what that 2 pi r dr is, that area, because it's independent. So I substitute that. So I can take the mu over 4 dp dx outside. So 0 to a, and 2 pi also is outside. 2 pi and r dr ur. So it's basically a square minus r square r dr. Okay, so let's say pi over 2 dp dx. So a square r dr. So a square r square over 2 minus r to the power of 4 divided by 4, and varying from 0 to a. So pi over 2 dp dx, substitute a is lower limit, it goes to 0. So a is a to the power of 4 divided by 2 minus a to the power of 4 divided by 4. So basically a power 4, so this becomes the quantity of flow. So pi over 8 dp dx did I do that right? A to the power of 4. Huh, what did I, yeah, what did I get there? Maybe I didn't do it right. Yeah, I got it right. Pi to dp dx. So dp dx I'm missing it. It's not minus, it should be plus. I don't know, it should be a square minus r square. So I made a mistake there. Okay, that's, so I'm correct here. So basically 4 is brought, so 8. As the pi comes in, yeah, this pi should be there. 8 pi, yeah. So pi over 8, so pi over to the power dp dx. Okay, so that's correct. So pi over 8 dp dx a to the power of 4. Okay, so now I want to look at what is the average velocity. So my average velocity, So let's go here. Here, my average velocity is going to be q divided by area. So my q is I over h dp dx. There should be mu, isn't it? Wasn't there a mu there? Should be mu there. Yeah, because mu was by mu, I think. Okay. That is my a to the power of 4 divided by pi a square. So mu over 8 dp dx a square. So that's my average velocity. So if you look at the my equation here, I don't want to make a mistake here. All right. So the average velocity, let me just, I divide by pi a square, I get a square over a, that mu comes in. I don't know why the mu came on the bottom. Let's see. Oh yeah, that's right. I brought the mu down because of the, I'm solving for u. So the mu came, so I think I made a mistake there. The mu is on the denominator. Sorry about that. Should be 8 mu here, not denominator. Because when I solve for the velocity profile, that is where the kinematic viscosity was there. I brought it down. So u is equal to r square over 4 mu dp dx. So this is the velocity profile, and then I put the boundary condition so that I can solve. So this should be a square minus r square. So because this has to be positive. So anyway, that's okay. Now the average velocity is given like this. So I can simplify my equation here. My average velocity is h square. I write it down here. My average velocity is going to be a square over 8 mu dp dx. Okay, so I can term the my ur. My ur is 1 over 4 mu dp dx a square minus r square, which we already proved that. So this is nothing but 1 over 4 mu dp dx a square is my u max. Okay, that's a max. So I can rewrite v as u max 1 minus r square a square, u max in the middle. But v, the average velocity is u max over 2, because you find the v was 1 over 8 mu dp dx a square. If you look at the v, 1 over 8 mu dp dx a square. Okay, this should be positive. I think the sign is all messed up here, but it's okay. Because everything is positive, obviously it cannot be correct otherwise. So I can represent the velocity profile as a maximum velocity in the middle minus 1 minus r square. This is nothing but the parabolic behavior of the velocity. This is the maximum. So I can term it as twice the average velocity 1 minus r square. Just making it simpler, that's all. So that rather than saying all about the dp dx, 8 mu and so on and so forth, that's okay. But we know that the average velocity v is 8, is nothing but minus 8 mu v over a square. So dp dx, the velocity, the pressure gradient is equal to 8 mu average velocity divided by a square. So I can relate pressure gradient dp dx in terms of viscosity, average velocity in the pipe divided by the A square. So if I convert that A to D, the diameter, so A, D square becomes, you have to multiply by the uh, 4. So 4 multiplied by 8 is 32. So I can relate, given the average velocity through the pipe, I can relate what will be the pressure drop across the length based on this equation. Okay, so that is how all the friction factor in a pipe, how do you calculate how much head is needed? If you have, maybe 55 meters of water is going at some velocity, how will I calculate the pressure drop? Obviously, I need to account for the pressure drop. So that is the equation for laminar flow. This is correct, 32 mu v over d square. Suppose in a practical case, it's not laminar, it's like a turbulent flow. So there is what is called a parameter called the friction factor. It's not the coefficient of friction. Friction factor is defined as, this is defined. In other words, I'm dividing the dp dx by the velocity head, which will be equal to the rho v, half rho v square. Average velocity v, half rho v square is a velocity head. If I divide that and multiply by d, I'm defining a friction factor F as the pressure drop multiplied by the diameter of this is the equivalent diameter, it could be hydraulic diameter, we'll talk about it, divided by the velocity head. So this is not the coefficient of friction. Coefficient of friction is the shear force divided by rho v square over 2, not the dp dx d. Okay, so if you put it for this particular pipe, you will find the coefficient of friction here is really the friction factor divided by 4. So don't consider that. So f rho v square is nothing but dp dx over d. So I can dp dx is given as 32 mu v over d square multiplied by d becomes, so f multiplied by the rho v square is 32 mu v over d. So in other words, I can find out exactly how much will be the pressure drop over a certain length. So I can calculate the pressure. So for a laminar flow, what exactly is mu v over d? If I multiply, in other words, this, what's the friction factor here? So it's equal to, okay, so let's do that. It's just, let me exactly do this case here. So dp dx is the pressure drop that's related to the f rho v square. So let's calculate, how do we get that 64 divided by qd? So let's just do that. Some reason it's not coming up. Okay, so let's just erase this. Okay, so what did we do? So we have the friction factor. Friction factor multiplied by rho v square over 2 is dp dx d, which is equal to, so what? How much was that? So let's just do that calculation. So let's just write it down here. So dp dx was 32 mu v over d square. Okay, so so f was f rho v square over d is equal to 32 mu v over d. Okay, so that's clear here, this one here. So f is 32 mu v over d divided by rho v square over d. So dd gets cancelled, so let's just do that again. Okay, so this is correct. So 2 becomes a 64. Okay, let's do it. So Fe square. So I'm relating that this is nothing but 32 mu V over D from the, no, this is the average velocity. Okay, the V is the, so I'm relating everything. So my F is 64 mu V over D divided by rho V square. So V gets cancelled. Rho over V is 64 nu V D. So what is 64 nu over Vd? What is this? That is nothing but 1 over Reynolds number, isn't it? Based on the D. So for a circular pipe, for laminar flow, the friction factor is going to be 64 over Reynolds number. Now, why do we need this? We need this. If I know the friction factor, I can calculate the pressure drop across a length. So let's just go back and look at it. How are you defining the, so dP dx, dP dx is what we want to calculate. The dP dx is equal to, you are relating that to a friction factor multiplied by rho v square. So what are we doing? The dP dx is F rho v square over 2 and multiply by L over D over a length. So the pressure drop, so here, look at this equation here. F is equal to dP dx over rho v square. All the negative and everything comes out. I think the negative should not be there, but just I will eliminate it later on. Because it's just, they're all positive, it cannot be negative. Okay, so how do we calculate that? So basically, I want to know in a pipe, in a laminar flow pipe, let's say. So my dP dx, so the friction factor was defined as dP dx, all absolute value, multiplied by D over rho v square over 2. Okay, that is, so when for laminar flow, the friction factor, the Darcy factor was 64 divided by Reynolds number. The Reynolds number based on the average flow, Reynolds number based on the diameter D of the pipe. Could be hydraulic diameter also. So our pipe is there. So this is a 2A basically. So I just simplifying it. So my objection is there's a long pipe of length L. How much is the pressure drop from across this whole length if average velocity is V? Remember, everything is parabolically distributed, but I got the average velocity and I'm defining F based on an average velocity. So let's look at that over the length. So basically I want to say dP dx or delta P over the whole length is equal to, okay, so F, okay, this is rho v square over 2, so dP d L over D. So they always say L over D parameter, depending upon, so rho v square divided by 2, so that's going to be my, so I will calculate my, so what is the depending upon the length, so depending upon the length, L over D parameter, and rho v square is always calculated. In other words, so given the length over the diameter ratio, so depending upon the velocity, maybe there is a constriction here. So velocity changes. So the friction is going to be much more here. The drop will be more depending upon the velocity there. So depending upon how much length. So I have a pipe. It's a transition to that lower diameter. du2, d1 here. So I know exactly how much drops here, L1, L2. So I can calculate based on the velocity. I can calculate I know the total flow is constant. Total flow is constant. So because the continuity equation, but the pressure drop is different at these each such sections because the velocity is going to be different. So that's how you use the friction coefficient. I'm sorry, the friction factor. F is a friction factor, not a coefficient of friction. See, not, it's not. Okay, all right. So let's say, where is it used here? Pipe flow is an important fluid mechanics problem, as you know. You might have, I don't know how much you guys did the some calculation in your fluid mechanics class, you know, in the beginning. So if I look at the correspondingly for a turbulent flow, such a friction factor has been experimentally found to fit this empirical curve. Here, the F is the same as the friction factor, F that we have. The Reynolds number here is based on the diameter. So this is not an explicit solution, equation here. It's implicit. It's inside left-hand side, also right-hand side is symbol F. So you make an assumption for F, find the new F, and then E over D. E is the roughness of the pipe. Okay. So they have plotted this curve. Sorry. So they plotted this curve here. Let's look at that. So all the friction factors, this is for a practical case. Look at the y axis. The friction factor F is defined as the dP dx, the loss of, pressure multiplied by d divided by rho average velocity squared over 2. So that's a definition of F. X axis is the Reynolds number based on the mean velocity that we did here. This um is the mean velocity d over v. It's a Reynolds number. So look at it here carefully. So what exactly all these curves? So depending upon the
Excuse me, sir.
Yeah, go ahead.
So can we close the class, please? We have a class at 9:50.
Oh, you have a class one?
Yes, sir.
You have a class in another. So you are leaving now?
Not leaving, sir.
I can't hear you. Please repeat it again.
At 9:50, in 5 more minutes, our next class starts.
Oh, okay. All right. So you want me to leave it right now? That's okay. No problem. I can let me take your attendance, and then you can leave. I can talk about it tomorrow. Okay. This friction factor, I can talk about it. So I'll stop recording. Yeah. Go ahead. It's okay. No problem.